My name is Rob Seeley, and I'd like to thank the First Nation Climate Initiative for putting this forum on. I think it's a super initiative, and thank you for the opportunity to participate. I essentially 38 years in the energy industry. I'm a chemical engineer by education, but worked in energy for all of my career, much of it with Shell Canada, some of it designing and building facilities in my early career, and then more latter part of my career as an independent consultant. It's interesting when you work in energy, it's how it actually merges from energy development to the climate issue and how much that starts to overlap what you do. And that really, for me, started about 20 years ago. As we were developing energy for Shell Canada, I became more and more involved in sustainable development. It meant more than just climate. It meant about engaging with communities, meeting communities' needs, meeting society's needs. So I have a passion for it, and here I am, maybe going back to school, and I'm hoping that everybody will enjoy this. I think the first part of it should just be fun. This is just about learning some stuff. We're not talking about policy here. We're not talking about positions and advocacy. We're just learning a little bit about climate science. So that's what the goal of this presentation is. It's been a while since I made this presentation. I was kind of reflecting when I pulled it out. 2011 I made this presentation. I had to go and update it all, but it's amazing how little has changed. Really, the messages are the same, the science is the same, but actually I made this presentation in Antarctica in 2011. The greenhouse effect, we'll talk about that. We'll talk about historical perspectives. We will touch on impacts. We're not going to go into the UN stuff here. That's going to be another presentation. But really just sort of the big ticket indicators, what's going on with our world and our globe. And then mitigation. What do we need to do to change course? And so again, this is kind of high level stuff. We're not going to do the deep dive in this first presentation. So first on the greenhouse effect, we hear a lot about that. And it's really just about understanding that in the world, we have the sun heats up our globe, and then it reflects off the earth, but it's trapped by these gases that are surrounding the earth. And those gases are a variety of things, water vapor being the biggest one, CO2, methane, many other things. We'll get to that in a minute. But it's interesting to note, without those greenhouse gases, our earth would be a flying frozen rock. We would be minus 15 degrees C, the whole earth, and we would not have a sustainable environment. So the climate, the same things that are keeping us warm and giving us a nice environment is now the thing that's putting our environment at risk. It is important to note that greenhouse effect is critical. And it's interesting also to note that the concentrations in the atmosphere have changed over time, up and down and up and down, almost like the earth is breathing. So this is talking a little bit about the gases that are in that, trapping us around the earth, and the water vapor, carbon dioxide, methane, nitrous oxide, and ozone. Those are the key ones that are there by nature. And then we've added a bunch, unfortunately, that are not helpful, and there's been other initiatives around elimination of these other gases. The Montreal Accord, it was the start of removing all of those refrigerant gases that have been a problem. We're not going to get into that today. We're going to stick with the main greenhouse gas actors, which are CO2, water vapor, methane, and we will talk a little bit about carbon black and some other things that are in the atmosphere. This is a chart that shows those different forcing gases. So carbon dioxide, other greenhouse gases was on that chart, ozone, carbon black. And then there's stuff that actually reduces the amount of radiation that's coming back out, and that's the effects of cloud cover, aerosols. And then of course land use, whether we're removing trees or not removing trees, has an impact on the amount of reflection from the earth. And volcanoes. The next big volcanic eruption could change everything, and depends on how big it is. And so we've seen that in the history of time. We haven't seen it, of course, in our time. Let's just talk a little bit about this carbon cycle, and where does the CO2 naturally go to and from in the earth? Well, what we see is that the plants, of course, are breathing in CO2 as they grow and expiring oxygen, which of course we need to survive. But then when the plants die and the leaves even come off the trees in the season, but more often when they're dying in their end of life, that carbon goes back into the atmosphere. Some of it, not all of it. Some of it is sequestered into the ground. Some of it goes back in the atmosphere. So the trees and the natural vegetation are roughly in balance. Same with the oceans. The oceans are also breathing carbon dioxide. They're emitting carbon dioxide and they're absorbing carbon dioxide depending on the level of activity in the ocean, the currents, the temperatures, the winds, all kinds of things. And then there's our stuff. This is the man-made stuff. And this is the stuff that goes up, but we don't have an answer to bring it back down like Mother Nature has for her oceans and her lands. Ours goes up and it just keeps contributing. So maybe we need an answer around that. What do we do with our emissions? How do we contribute to the balance to get it back? But it's worth noting that this number is 28. If you look at these kind of add up to about 800. So Mother Nature's ability to absorb and emit carbon is significantly bigger than man's in the general cycle of things. These are big engines. We're a small engine, but we're not doing our part on the reduction side. Now we're going to get into a short history on global climate science, and surprisingly enough, this started way back, and there was a Swedish scientist, Arrhenius, and other physicists were writing papers about this in the 1800s. They had linked the CO2 concentration in the atmosphere and the greenhouse effect to global temperatures. So they'd kind of put the math together roughly there. The next thing that happens in our climate science, we have other theories that come along in the thinking with the power of computing. But I would say the big breakthrough comes in with Charles Keeling, who decides he's going to monitor the CO2 concentration in the atmosphere at the top of the Mauna Loa volcano in Hawaii. And he sets up his gear up in about 1958. I think he got some grants and some money. And he set up a research lab on the top of that volcano in Hawaii in 1960. And then he monitors the CO2 concentrations in the atmosphere all through the seasons. And he monitors it for years and years. But it doesn't take him very long, only a couple of years to see what's going on. And he assembles over the 40 years a plot of the CO2 in the Earth's atmosphere. But it's interesting that each year that CO2 goes up and down in one full cycle. And it's almost like the Earth is taking a breath. So it's, I think, the Mother Gaia theory that the Earth is a living organism. You know, this is sort of coming out in his analysis. He's seeing the CO2 going up and down, almost like with a breath, our annual in, breath out. And it was interesting that those cycles are very closely linked to the Northern Hemisphere's seasons. And the reason they are is because in the Northern Hemisphere, we have more land mass. We have a lot of land mass for ice and snow to accumulate in our winter season, and that becomes a reflector. But we also, with more land mass, have more vegetation, trees, and those trees are on a seasonal cycle. The leaves fall off in the fall, they go on the ground, the trees stop absorbing for a period of time, and so there's a dip when they're not absorbing through our winter, and then it goes up as they grow again. And then the next piece of information that I found extremely interesting in this journey is what we call the Vostok ice cores. And so they started drilling in the ice of Antarctica, and they started drilling down to try and learn about climate science. And it was about 1980 they started the drilling. They got to 2,000 meters, and then they get to 3,000 meters. And at 3,000 meters, they're getting about 400,000 years of information now. And so through that information, so whereas Keeling was on the top of the volcano, he had his 40 years of data about climate science and climate cycles. These guys came back with 400,000 years, just like the rings on a tree. When you cut the tree, you've got the rings on a tree telling you if it was a fast-growing season or a slow-growing season by the tightness of the rings. That's what they were finding in the ice cores. the ice cores. Was like a ring on a tree, and it would show them the compression of the year would show them what kind of CO2 temperature was. It was basically oxygen isotopes were the key measure for CO2 temperatures. And then based on that, they plotted the CO2 on the big picture. So rather than the little, annual cycles, the breaths, these are the big breaths. And so this data goes back 400,000 years based on Vostok ice cores from Antarctica. And what it shows is that, yes, we're at the top of a warming cycle. In fact, we're even warmer than that. We're warmer than we want to be. But these are big cycles that happen naturally in the Earth, and they're happening roughly every 100,000 years. There's a warming cycle. And then there's an ice age, and we do know, our science tells us that we came out of an ice age, and the ice age was roughly 80,000 years. We have an ice age every 100,000 years is what it was telling us. And so when we talk about climate change, of course we all agree in climate change, because the climate is always changing. It's what happens in Earth. It's what's been happening for the last 400,000 years. It warms up, it cools down, it warms up, it cools down. And then they said, well, maybe we can get some more data. And so they went drilling in the ocean's floor. And so by drilling in the ocean floor, they were able to pull out sediment, again, sediment layers, just like the layers in a tree, sediment layers from organic matter. And again, they do a deep analysis on isotopes in the organic matter, and they can learn about the temperatures going back even further. And so from these sediment cores, they took a crack at estimating what it looked like for 5 million years. Now, my understanding from the science is it gets pretty flaky because everything is so compressed that you really can't determine the difference in many of these years. But at least I think what they agreed to do is try and extend the view from 400,000 to about 1 million years so they could get more of a composite interest. And this is basically a picture of the samples and ice cores that are in storage. And they've built a composite of 800,000 years. And I would say this data is half of it is Antarctic data, 400,000. The other half is the benthic forans off the floor of the ocean. It's another 400,000 years. So they have roughly 1 million year view of what's going on. But again, it shows the climate warming and cooling and warming and cooling as we know that the natural cycles of the Earth. And I'm not advocating anything. I'm just going through the science here. And because we still have a problem. Believe me, we're going to get to that. But this is an interesting part, that the Earth has been going through these big cycles in time. And of course, man's history is really only maybe in the last 10,000 years, but really, I don't know what the population of Earth was for man coming out of 100,000 years ago, but I think it was pretty small, maybe 100,000 people, whereas in 1900, it was 1 billion people. So maybe there's just one more thing on this deep science, and then we'll kind of move on. People were trying to figure out what's causing these big cycles. Like, why does this happen? And this is where the science, I think, is a little gray. I wouldn't say there's a, yeah, I got it. I figured this one out. But there was a scientist by the name of Dr. Milankovitch, and he did, his research really looked to more the astrological reasons that this might be happening. So Earth's part of a solar system, we're going around the sun, and he basically had a mathematical formula he was looking at different factors, forcing factors based on Earth's orbit of the sun, and he had 3 factors. One was called eccentricity, which means the Earth's going around the sun is not perfectly round. It's actually it's an ellipse, and it's an ellipse that changes shape over time, over intervals. And those intervals are really big. The change of shape might be every 20,000 years, 50,000 years. He's got this in his mathematical formula. The second thing is the tilt, that the Earth is tilted, and that tilt moves back and forth. It doesn't stay at the same tilt forever, and that it's moving through these big cycles in time. And then the third thing is there's a wobble. And so it's not only one thing to have the tilt, but it's kind of pivoting on an axis like a top slightly differently. So he pulls together these mathematical formulas for each of these three factors: the ellipse, the tilt, the wobble, and he's got them in mathematical formulas like this over time, because he's mapping them over time, how fast. So these are big, tens of thousands of years, and he gets this composite thing called, what does that mean to Earth's temperature? And so when they mapped the solar forcing formula over the peaks in temperature, there were some correlations. And so these correlations were, and I wouldn't say this, there's many factors affecting Earth's climate and temperature, because we did go back to things like volcanic eruptions and all kinds of things that can disrupt this. But this might be the fundamentals of why we're having the big cycles, but it's not so dominant. There are other factors at play on Earth that can overshadow it, and we'll get to that. And so back to the big cycles and our 400,000 years of data and CO2. And so they had temperature and they had CO2. But it's interesting, because when we come out, we are in a warming trend. We have been for 10,000 years. But now our CO2 measure is somewhere we have not seen in those 400,000 year cycles. In fact, they're saying we haven't seen this in more than 650,000 years, a CO2 level this high. So we're saying, now we're getting out of the normal pattern of Earth's warming and cooling. And what does it mean? At worst, it's a dangerous experiment, or at best, and at worst, we have a major problem.
Early on, you showed that there's a number of different systems at play, large macro systems that are emitting CO2 and absorbing CO2. And by comparison, in the diagram you showed, the anthropogenic sources of CO2 were fairly minor in scale. And now what this is saying is that adds up, and we have now actually achieved levels of CO2 in the atmosphere that have hitherto not been seen before in the data.
Yes, there's a couple of maybe caveats to that. One is we continue to add more CO2 to the atmosphere through our energy patterns and our energy use. The other side of it is, in 1900, we were only 1 billion people. And now in 2019, we are 6.5 billion people. And to accommodate those people, we are removing large tracts of land for agricultural purposes. And we are removing large tracts of land for building cities and other kinds of development. And as we do that, we're reducing the ability of Mother Earth to absorb the carbon. So it's kind of, there's two sides to the balance sheet. We can't always look at the one side, what's going up. We have to look at the other side. What do we also need to do to help absorb the CO2 and bring it back down? Which leads us to the next body of science, which was around 1988. They formed the Intergovernmental Panel on Climate Change. And this was to bring, now we have a problem. We know we have a CO2 issue in terms of it's above historical highs. We need to dig into this further and try and understand what this means to our planet. And so that all started in 1988 with the World Meteorological Organization and the UN combining resources and pulling together this Intergovernmental Panel on Climate Change. And then they've put out a series of reports, and we will see a little bit about this most recent report, the IPCC special report around 1.5 degree, holding to 1.5. We're going to see some stuff on that here today. This actually was, so when they did the fourth report back in 2007, I think these findings weren't new. I think around the impacts of increased CO2 in our atmosphere. What is it doing? Are we warming the planet beyond historical trends? And if so, by how much and how fast? but it was saying, hey, this report back in '07 was clearly saying, yes, we are warming faster than historical trends. Here are some of the things we're seeing around ice melt, snow melt, et cetera, et cetera. And mitigation will be required. We need to change our energy transition. So we're going to talk a little bit about, let's just have a look at some key indicators on impacts to say, do we have a problem? Because the IPCC is saying, yeah, we have a problem, clearly. But I actually turned to NASA, and NASA has a very good website. It's called the Goddard Institute, and they collect a lot of data on the Earth from space and space satellites. And so I pulled some stuff from NASA here in three kind of major themes. One, the first theme will just be on global temperatures. The second theme is on surface ice melt, and that's Arctic and Antarctica. And then the third is sea level. So we're just talking about what I would call the key indicators. We're not going to do a deep dive into terrestrial ecosystem impacts and all that sort of stuff at this point. I just wanted to pull a few examples out. This is their chart from NASA on the recent historical trends in global temperature. Now they have to use sophisticated modeling because they're measuring temperatures in oceans, they're measuring temperatures on land, and then they're trying to pull it all together. They're thinking about seasonal averages and how do we get like a temperature for the year. It's pretty, there's a lot of inputs. So it also means when you're doing that kind of modeling, there's a lot of assumptions. But regardless of all of that, what I do see is that they follow some of those patterns that Keeling saw on the volcanic, on the Earth's top of the Hawaiian volcano as it breathes in and out. So we see it going up and down every year. And what we do see is that, going back to 1880 to 1940, so about 60 years, there was kind of going nowhere. Then actually in 1940 to 1975, the globe actually cooled. And I don't know, we've got some people in the room my age, but I remember growing up in 1960s and 1970s and walking both ways into the wind to school and snowbanks this high, and it was cold. It was harsh, and that's what we remember as kids growing up. We were in this period of time, and it is a different world now, because as of 1980 we've seen this temperature gradually increase. Now this is in degrees Celsius, so we're saying from 1975, I'll call it 79 because I'm going to show you some data, to about 2019, 20 years we've seen that thing, the globe warm roughly 0.8 degrees Celsius. But 0.8 degrees Celsius we'll see matters. And now this is, NASA has a nice time lapse video. You can go in there and have a look at it. But basically this is kind of where the warming trends were in 1979. And so you can see that it's starting to impact up here in the Arctic and Alaska in 1969, and a little bit over here in Asia. Then we jump forward 20 years to 1999, and where it's impacting has gotten significantly broader than just the Arctic. Those same areas continue to be the trouble areas, but there are other hot spots on the globe. Now this chart, I should add, is in degrees Fahrenheit. Okay, so it's not degrees Celsius. So you almost divide by 2 to get degrees Celsius. But where it's yellow, it's saying that's 1.5 degrees to 2 degrees of Fahrenheit. Could call it 1 degree C. So these are some of the, so again, that's back to the 0.8. It's close to the 0.8 number we just talked about. And then in 2018 numbers, I think the most important thing from this chart, according to NASA, is it's the Northern Hemisphere. Remember we talked about the Northern Hemisphere matters? And that's where we're seeing more of the warming. It's in the Northern Hemisphere. And then what they also do, this is a chart trying to depict, well, what if it was just natural warming? How do we know this isn't natural, part of Earth's 100,000-year cycles? And so the scientists were trying to differentiate what's normal and what's man contributed by man. So that was this effort here. And then I think what I'd like to do is switch from the temperature data to the poles of the Earth. So let's look at the Arctic ice and let's look at Antarctic ice. This is the Arctic, and so this is 1979 in what I think they would call summer ice melt conditions. So you have to look at what does it look like in winter and what does it look like in summer. And so I think this is the summer ice melt condition of the Arctic, and that's what's frozen in 1979 according to the satellite data. And then you jump ahead to 1999, and you can see that we have some open ocean showing in summer, and then again into 2019. So you can see that there's a significant reduction in sea ice surface based on that data set. And then kind of there it is, red line versus white on the change, 1999 to, actually this is 2010 data. So another thing about that, so it's one thing to lose that ice for maybe the habitat, and everybody's concerned about impact on habitat, but we have another thing called feedback loops. And feedback loops are important because they can accelerate this warming or decelerate this warming, depending what they do. And in this case, the loss of sea ice is an accelerator. It's a feedback loop because instead of having, if you think about that sea ice being a big reflector on the top of the Earth, and then the sun's radiation comes in and boom, and it ricochets back off, and some of it gets trapped and some of it makes it back out to to space. Well, if we reduce the size of that reflector by a third, it's only logical. We're reducing the amount of reflecting, which means that energy is now hitting the open water and the ocean and being absorbed by the oceans. So the energy is not getting reflected back out. So that in itself can start to accelerate the warming. Now it's going to start to warm the ocean or generally the climate faster. So that's called a fast feedback loop. And there are other examples, and I think the other example would be the tundra, the tundra of Canada. And that frozen ground is important because it's also a reflector. In the winter, when it's all frozen and covered in snow, it's a reflector. And as we lose that frozen permafrost, then the permanent snow or permanent reflection, some of it we'll lose again some areas. I haven't got exactly the math on that, but it's the same philosophy. And then they've got data on Greenland and the amount of ice melt there over essentially roughly the same time frame and mass variation. They're showing gigatons per year of ice melt, of accelerated ice melt. So we have that data as well. These are Northern Hemisphere data sets. And then if you skip to Antarctica, it's a little bit different story because again, we talked about the Northern Hemisphere and the tilt of the axis and everything, but I think in Antarctica there was, for a period of time, even in the recent history between 1995 and 2005, it almost looks like the ice is building mass again. So we're not in as significant a change there. However, they are still trending. It is trending slightly warmer, and that would likely be a combination of ocean temperature and air temperature. And the ice mass, again, on the fringes, we're losing ice mass. Now that, I might add that ice mass is not as critical as Greenland to ocean, to sea levels, because the ice is already in the ocean. It's kind of like the ice cube in your drink. When it melts, it doesn't make the drink level go higher. It's when you add more ice into that drink that the level comes up. So a lot of this ice in Antarctica is already sea ice and floating. So it's not the same concern as the Greenland ice, which is on land and is ice and is melting into the ocean. That is a much more significant issue for sea level rise. And then I did have an opportunity to go to Antarctica in 2011. I was with a group called 2041, and it's an NGO group that is basically advocating around the Antarctic Treaty. And Antarctica is protected under a United Nations treaty from development. And it's also in that treaty, it says nobody owns Antarctica. And it's interesting because Antarctica is big, like it is the size of Australia. And to say that we have a continent on Earth that nobody owns is pretty unique. And so this group 2041 is all about raising awareness, and like, we want that treaty renewed. We don't want everybody going down there drilling for oil and gas or exploring for minerals, looking for lithium for their batteries. We don't want that. We want this particular continent to remain untouched. So that's 2041's mission. They were taking us down there to show us the continent and make us learn about it. It was a fascinating place, but what we did get to see was on the what they call the northwest part of Antarctica is the peninsula, and that's the part that's warming the fastest, just the way the winds go around Antarctica. Antarctica's like an island right on the bottom, so basically the prevailing winds are circular, and they come over those mountains and sweep down across the big ice plateaus called the Weddell Sea, and that's where the big ice chunks are breaking off. And this was called Larsen B. I don't know if you guys ever heard of Larsen B, but it was a piece of ice about the size of Prince Edward Island. It was big. And so it broke off in, I don't know, probably in the 1990s. And there are other chunks that are breaking off there, but they're already in the ocean floating, so that's a little different. But we had our ship, we were going through these big, massive things that are, 10 stories high, and we got a scale of it. And then the captain quickly said, "I'm getting the hell out of here, because this is where Ernest Shackleton was frozen in the ice." And he could see all the ice coming in, and he hightails it out of there because he doesn't want to be a statistic like Ernest, or a storyline like Ernest Shackleton. And so, but at the same time, it was a beautiful place, as our North is, as our Arctic is. We could take the same kind of pictures up there. And so this is more data on sea ice, but we don't need to go there. The last piece of data that I want to pull from the NASA site is about sea level. And it's interesting, a lot of these flooding issues come with the big storm surges. They're not just naturally creeping up. It's when you get a big storm that they notice the difference in sea level. But this is the composite data, a gradual warming. And I think, if you look at the historical stuff, this kind of sea level rise is probably natural. Because if you go back to the natural cycles, in this period of time, the CO2, even up to the 1920s, we're pretty normal in the normal cycle. So there's kind of the oceans are generally on rising as a result of natural climate swings. But then, of course, what we see is those lines start to get steeper and steeper, that they're rising faster. Now, these numbers are pretty small, 3.2 millimeters a year, average 1.8. I'm trying to get, what does that mean? It's like, okay, so in 10 years, that's 18 millimeters. Well, 18 millimeters is half an inch. So half an inch every 10 years, something like that, or maybe a little more, 3/4 of an inch. How's that? My math, Paul? Am I okay on that? I'm trying to guess. It's not, but you keep adding it up and adding it up and adding it up. That's it on the climate impacts. Those are high-level things. We're going to see a lot more what I call specific data when we get to the UN thing. And then it just talks about the risk. Where are we going to end up with all this? We don't know, but if we end up here, we know we have a problem. If we end up at 5 and 6 degrees, that's not where we want to be, because that creates issues like this, and like this. So, what do we think of all this? I think we need to, of course, everybody in this room wants to shift the outcome, and we want to get ourselves knowledgeable in this whole business of climate and climate science and energy transitions and carbon sinks and carbon stores. And we want to shift this down to the 1 to 2. So that's what Paris is saying. Not 2 to 2.5. We want to shift it to the 2 and 1.5. And this brings us to the Paris Accord. And of course, they're meeting in Madrid now, and they're going through some of the details of that were not resolved in the last meeting of the parties. And the big thing that came out of Paris was well below 2 degrees. That's where we want to be. The other thing is that developed countries, and that's what we are, we need to take the lead, okay? Because we've been part of the problem, and other countries want to rise up and have their opportunity for a better life and a better economy and a better way of living. And so with that comes carbon emissions and activity and energy. And then there are a number of things they talked about in there, taking reductions, financial resources, but they also talk about sustainable development, and I'm going to get to that as well, because it starts to talk about access to energy. It's not all about energy as the problem. Energy is also a solution for sustainable development in our world. We have 1 billion people on the globe without electricity. We have 2 billion without reliable electricity. And then if we talk about clean water, how many billion do we have? And so when you get into the sustainable development discussion, it's like energy is a big way to lift people's quality of life, but at the same time it brings this carbon footprint thing. So how do we make both sides work? This was a piece that talked about, I think the IEA stuff might cover this later today, but basically it says if we stay on the same track, we have gigatons of CO2 ending up in this pink band up here with roughly 3 to 3.8 degrees of warming. If we did everything that the countries that have pledged at Paris in 2016, if we did everything they've committed to do, including Canada reducing by 50%, I think in Paris, what was our commitment in Paris? 30% by 2030 or 40, and then 80% by 2050. I think those were our commitments. So that kind of stuff, but there's only a part of the world making these commitments. There's a lot of the world not making these commitments. But if we did make those commitments, met them all, we'd end up here. But it's pretty clear from the modeling that we need to do better even than the Paris commitments. And we need to get more countries involved in this journey and more cooperation. And then this is essentially just a breakdown on global emissions, the 38 million tons. Electricity, industry, transportation, agriculture. I think people have seen these charts 1 million times. But it's interesting that power, electricity, which is 24% of the globe's emissions in Canada, actually are quite small. We have 80% renewable electricity or low carbon electricity in Canada. Between our hydroelectric power, our nuclear power, and our new renewables, we're actually one of the world leaders in this area. So this, if I look at Canada's piece in here is quite small in our percentage. Probably transport and buildings are the big thing. We got big distances and we have a big country to get around in. And the other thing that I'm noting with Canada when we get to Canada's emissions are, we're a net energy provider to the world and resources. And so if you mapped out all the countries, I'm going to go to this one, all the countries in the world and where do the emissions come from. Here's Canada in here. This is the world's emissions in a big box. And here's Canada's emissions. And here's Asia's emissions. Okay, now a lot of stuff gets lumped into Asia. You can see Japan, Iran, Saudi Arabia, the Koreas, Thailand, Kazakhstan, many other countries are linked in there. But there it is, China and India, big chunk of those, USA big, and then EU and Russia. But we're actually providing energy to all these other countries, and that's part of why our footprint is so big per capita. Everybody says, oh, Canada's so high per capita. Is it because we have a big country? Is it because it's a cold climate? Yeah, and it's also because we're producing resources for the rest of the world. This particular source is called the Global Carbon Project, and I think it might only be from combustion. Whereas if you look at some others, you say maybe there's a contribution from land use change. Okay, I cut down X percent hectares of a forest or whatever, and the land use change contributes to an emission. So I think that might be the difference between this number and some of the other numbers. They've added the land use change in. So okay, we expand a city, cut down trees. We cut down an area for more agricultural resource. Those numbers start to get added in.
Okay, so then of the 38 billion, which is essentially energy,
Combustion emissions, yeah.
what proportion of that is coal?
So coal is, in this slide, is the brown stuff. I would say it's about, if we're at today, in any one of these scenarios, this is today, the beginning of these charts. So today, I think coal is, I think they say it's about 24%, something like that, 20%. That's in energy terms. Is it? Versus emissions terms.
It's Dave, can I comment?
Yes, please.
I think you're in the ballpark for global emissions, but what's an interesting way to look at the coal question, I think, is its percentage as part of power generation and electricity, because when you talk about emissions overall, you get muddled up with the transportation sector and how big a contributor that is net. But one of the things that I think is fascinating when you ask that question about coal is just looking at what's been the history of coal and where is it going vis-a-vis those nationally determined contributions that countries are trying to make. If I can share my screen for 1 sec, I'll show you guys one thing that I like looking at that really kind of speaks into that story. And you can see on the chart, this is like installed operating coal plants. What's been happening, this line here is China and what's been going on. You know, Europe and the United States have been actually decommissioning coal plants. But what's fascinating is watching what's happening over time. So I'll just run this through a progression here. And you can see I'm starting in the year 2000 up here, and just watch what happens on the map. So what you'll see is the operating is yellow, and the ones that are just new in any given year are the orange. And you can see what happens as you kind of track over time, the growth of things going from under construction into new and operating. And as you keep going, you watch what happens on the map. And if you scale it right to the end, here's what I think the opportunity space looks like. Not only is it real and true that new coal plants in China especially, but India is like right behind them, going into operation like crazy. But if you look at Africa, you look at the Middle East, you look at especially China and India over here, these are coal plants that are either under construction right now as we speak, and there's all sorts of data out there. There's literally, over 800 coal plants under construction right now, and more that are planned. And the reason is quite simple, is these are the areas of the globe that are struggling out of energy poverty, and they will go to, they will struggle with that balancing of climate imperatives versus energy security, and this is the opportunity space. So we hear, when we talk about what can we do over here to help these people over there, and we talk about the opportunity of displacing coal, I mean, it's not made up. It's not an imaginary thing that this level of coal plant is either planned or under construction as we speak. And so there's not much we can do about these ones that are in operation. I mean, some of them might be opportunities to switch fuels, but honestly, most of them are installed. They're going to run their life. The challenge is all of this purple and all this purple on the map. How do you convince them to switch to a cleaner alternative as part of a transition? And the other only point I'll make is that I hate it when this conversation then switches to, oh, well, we should just do windmills or solar farms instead of a gas plant to displace these coal plants. And my answer to that is very simple, which is we need it all. We need as much wind and solar as fast as anyone can possibly build it. And it's not going to change this picture, because this is baseload firm power generation, and this is needed in addition to all of the wind and solar and everything else we can build. Thanks.
What do you mean in addition? Dave, what do you mean in addition?
I mean that it's not a question of should we build gas plants instead of windmills. We need them both as much. We need all the windmills and all the solar plants we can build in the world. We need to do that as those are the world energy needs. Like, it's not debatable that the world need for energy is growing. The only debate is how are we going to fill that need. And when it comes to electricity, not when, we're talking about electricity and how we generate electricity as part of that mix, there's a need for all of it. We need solar, we need wind, we need firm baseload generation. And what I think we should not be doing as part of that story is coal. Coal is the thing that's going to tip over the picture. And it would be better not to have any emissions, but in the meantime, it's the worst, dirtiest thing we've got to get rid of first, and that's coal. And when you look at pictures like I just showed you, like, that's indisputable that the world is right now continuing to consume coal. It's tapering off because of Europe and the US getting out of coal, and Canada, but it's increasing like crazy. Just look at the chart on the left. The increases are dwarfing the shrinkage.
Hey Dave, it's Chris here. That was going to be my question. Are we able to meet the global demand without the use of coal, or is that some use of coal also going to be required?
I like to think, yes, we could, but it's going to take an effort like fighting World War II level of effort by the leaders of the world, but it's possible. It's just the problem we have is coal is cheap. That's the problem. And so, our challenge in Canada is to show the world we can at least produce clean LNG as cheap as other LNG alternatives. And then if we work collectively together and really get at it, I think we can get the price of gas close enough to the price of coal such that at least countries that give a damn will make the clean choice. And you couple that up with windmills and solar farms and hydro and nuclear, all of it, then yeah, I think we could push coal out, but it'll take a level of leadership that's crazy impressive versus what we're seeing right now. That's why I'm so excited to see this table emerging, because what it's going to take is this level of coordination and effort.
So maybe I could ask you to take a slightly different angle on the same sort of question. You and I have had this conversation about how difficult it is to persuade, for one country to persuade another country to do anything. And if we're going to try and persuade China or Japan or Korea to switch from the coal they're burning now and the plants they're building now to burn more coal to LNG from Canada, how do we do that? And what's the role of the leadership of these nations in helping Canada to do that?
Well, I think it starts, for me at least, it starts with
Announcing participants.
working with partners and countries that actually genuinely want to solve this
Participants
problem.
exiting.
And that doesn't, there are a lot of those out there, and many, like Japan's a great example. I mean, the citizens and the people of Japan don't see things very differently from Canadians. They're basically on their government's case, like much the same way as Canadians, to say the status quo is not good enough. And so my view is we start with countries like that, and we prove it's possible. And that's why LNG Canada is such an exciting development. Like, we have shown the world, or trying to show the world by building that you can have a project that's the cleanest project in the
Announcing
world,
participants.
and it's still investable, and it still makes money for people, and it provides these opportunities for local nations and jobs and the economy and all those things. And we've got to, because if we can't show the world we can do this, what happens is the counterpoint gets made. What we prove to the world is, well, it can't be done, so we just got to do what Qatar does, or Mozambique, or Australia, and just not give a damn. Just let the emissions be what they are, and who cares if our LNG is hugely contributing to the problem. that matters is that it be cheap. I don't think that's true at all. I think you can do both, but the challenge, to answer your question, is proving that to be true. And this is where we started this meeting. You talk about where's the environmental community and why aren't they at this meeting? Like, why aren't they our biggest partners in this conversation is a continuous mystery to me. Because what's the alternative? The alternative is to prove to the world, well, you can't do this right. You can't be clean and green. Like, my dream is net zero emission, net zero LNG. It's still going to have emissions when you burn it somewhere, but the creation of it, we should be able to do with net zero emissions. That's my goal. And I think it's achievable. And if we did that, it would be a huge challenge to the rest of the world. Well, if Canada can do it, why can't you? And then we can at least begin changing the dialogue. But right now, we're fighting, like the environmental community generally is fighting us on this, and it makes no sense to me.
So I just looked it up.
Sorry, I took over
Thank
the
you.
meeting, and
No.
I gave you your slides back, your slide control back, but I couldn't, you know me, I gotta give my 2 bits.
No, that was great. Thanks very much. And just to be clear, our communications with the Pembina Institute have been very positive, and they are looking forward to engaging with this process. And they were unable to be here today. Karen Tamu is in Madrid, and the others that we've been speaking to are looking forward to engaging with us in the new year at sessions like this. And so what we have communicated to them is very much what I said at the beginning of this session, which is that the nations want to hear from everybody. And it's good that we've recorded this, because as far as I could tell around the table, for the scientists that are around the table, nothing's been said here that isn't a good representation of the facts. And if they take a look at it and they want to add something, we're sure interested in what they want to add.
You know, we talked a lot about climate and CO2, and now we're talking about, yes, it's linked to energy, and what does the world's energy system look like? And so we have a snapshot of the different energy inputs. And I think what I'd like to do with the end part here is talk a little bit about where we need to go. Our energy system, it is global, it's vast, and there are other factors at play, and that is, we talked about global population, the world's rising population. We talk about people wanting to rise their standard of living. We've talked about increasing CO2 as you increase energy needs, and the need for almost, I think we need roughly half the CO2 or less that we have today. Well, we need to go to net zero, we know that. And then we are going to hear more this afternoon a little bit about, or this morning, about the International Energy Agency's scenarios. This is a snapshot of the energy portfolio to 2040 under 3 different scenarios. And sustainable development scenario is how do we meet that 1.5 and 2 degrees C goal, but also meet some of the key goals of the United Nations Sustainable Development Principles, access to energy, clean water, those kinds of things. So that's in that scenario. And the IPCC report that was there has a lot of work on this as well, and they take that significantly further. They look at all 18 sustainable development criteria and start to overlay that onto the energy pathways to try and figure out what's the best way to get there, but also meet these other goals of the world. So either way, we know we're going to still need more energy with less CO2. And what are our options to fill this? Getting to Dave's point, we'll need to explore all mitigation options and to achieve this 1.5 degrees C. And so Dave was talking about the first box, a shift to natural gas in Asia. And the only way they can shift to natural gas is build a pipeline from Russia, which they're doing, and get LNG by tanker from North America, which seems to be more and more prevalent between US Gulf Coast and us. That's how we get gas over there. Nuclear power, incidentally, there's an article in the paper today around small modular reactors. And I did have an opportunity to work in my post-Shell career as a commissioner for the Canadian Nuclear Safety Commission. And in that time, we permitted re-permitted the Chalk River Nuclear Laboratories. And I don't know if you know anything about how much brain power we have in Canada at the Chalk River Nuclear Laboratories, but this is the place that developed the CANDU reactors that are built in Ontario. Then they moved that technology to China. Then they're providing 40% of the world's medical isotopes from that laboratory. And they're exploring paths for hydrogen, and now they're exploring small modular nuclear reactors. Interestingly enough, there's about 1,600 employees at the lab, 900 with PhDs. Anyway, so Canada's got quite a history there. And then the other side of that whole piece is we have uranium. We're supplying, like, I don't know what percentage of the world's uranium, but it's coming from northern Saskatchewan. Renewables, we know that's going to be a big part of our future. Biofuels, carbon capture and storage. I happen to know a little bit about that one, having built one over in Alberta at the Scotford refinery. And then we'll talk about some of these other things, road transport, electrification. But there's the other side of the balance sheet. And that's about how do we reduce the balance sheet too. It's how do we reduce what we use, but how do we actually pull it out of the air?
Could you explain a little bit more on the carbon capture?
Yes. Yeah. So carbon capture, I mean, this is referring to technology that is bolted on to facilities. So let's say it was a natural gas plant, and that was pulling natural gas out of the ground, and say in the Horn River, and there's a lot of CO2 in that gas. Well, they remove it because we don't want it in the pipeline coming down to burn at the burner tip at my house. They remove it at a gas plant, and it goes into the atmosphere. So they're emitting CO2 at the source. So you can bolt on technology to capture that CO2 with a solvent, and then you compress it, and then you can put it back into the geological reservoir. What I like to say is where oil or gas came out, there's porous sandstone rock down there where the oil and gas was trapped. There's also a great place to put this CO2 in those same porous rocks. So that's kind of what carbon capture storage is all about. It's really about capturing CO2 from industrial sources, whether it's a gas plant or a power plant. Coal-fired power plant in Saskatchewan has this. And then you capture the CO2 before it goes into the atmosphere, right off the stack. You compress it. When it gets compressed, it's almost like a liquid, almost like water it looks like, but it's 2,000 psi. And then you can put it back into the ground, into sandstone rock that's porous, just like an depleted oil or gas reservoir, or a porous sandstone rock formation. So that's carbon capture and storage, and we see the IPCC talking more and more about it, because it's one thing to reduce what we emit, but we need to start and this is one technology to do that. But you could take this technology one step further. And so a guy named Dr. David Keith has got carbon engineering in Squamish, and his idea is to suck carbon dioxide right out of the air, okay? And then with these big fans system, and then again, compress it and liquefy it. And now, if you actually took that and put it back into the geology, you're sucking carbon out of the atmosphere. We're going backwards now. That's the other side of the balance sheet that we're talking about that's needed. So you can use this technology also for not only capturing industrial emissions, but bolting it onto an idea like David Keith's and sucking carbon dioxide out of the atmosphere and putting it back into the geology where it came from.
I just want to make
Yeah.
ask a question,
Yeah.
which you and I have discussed before, and it's a bit provocative, not expecting you to answer it right now. But I sort of flagging it now, and I wanted Tyler to hear it because he's going to be involved. He used to work for the International Energy Agency before he took his current job. And it has to do with the tension between renewables and gas as a transition. And a number of the folks out there in the world who care about this stuff, who write, there's articles that Shannon and I have dug up that say exactly what I'm about to say, are concerned that in certain locations at least, there could be a competition between gas, even if it's clean, and the development of renewables. And when you build gas infrastructure, you don't build it for a few years, you build it for a long period of time. And if you have the option over a 5 or 10 year period to either build gas infrastructure or renewable infrastructure like wind and solar, particularly with battery power coming on stream, the world's a better place. You can jump right to the renewables and skip the gas. And I know that I'm talking to a whole bunch of people that are in the gas business. So I'm not trying to make friends, I'm just trying to bring up an issue that has to do with what's in the minds of some of the folks that aren't well represented here today, that we do want to talk to. And those are the kinds of things they're going to say. And in some instances, maybe they have a point. And in other instances, they don't. But I want to just get it out there.
Yeah, and I can't say, I'm not going to jump into it other than to reiterate Dave's point, and you'll see it in the IPCC stuff and the IEA stuff. We need to do all of these things. It's not about one thing or the other thing. And what we do know, for example, in those scenarios, you see that gas is actually fairly flat. We don't see a huge growth in gas under the Sustainable Development scenario. But what we do see is that the countries who need it don't have it. And we got to get it there. And so even though the growth doesn't increase, where it's being burned changes, and we got to get it to them. And the other thing about renewables versus coal versus gas is that'll be driven by policy. Gas is way more expensive than coal, and it's actually more expensive than renewables now in those countries. So they're building renewables like crazy in China as well. Dave just talked about coal, but there's also a thing about renewables. So to me, it's going to be policy decisions drive it, not just a cost thing. And then renewables, you and I know the wind only blows roughly 1/3 of the time, statistically, to enough to drive a windmill to make energy. And the sun only shines, particularly in this part of the world at this time of the year, I don't know, is it even 8 hours these days? Not a lot. So what do you do in the rest of the time for energy? Well, China's building more coal. We just saw it, 800 plants. So they're going to need to complement renewables. You can complement it with coal or gas or something else. But gas is a good complement to renewables, very good complement, because it can easily be turned off when the renewables come on, whereas a coal-fired power plant just wants to run steady and long. So I think, in the end, I think gas will complement renewables. It's not a takeaway, but I think the big message is we have these options on technology. We have a number of things we need to be thinking about for sinks, putting the CO2 away. This is restoring forests and forest cover and managing our forests. Same for doing on cropland. This is the CCS thing we just talked about, capturing CO2 from industrial plants and putting it onto the ground. And then they have two other types of sequestration. They talk about biochar and enhanced weathering, which I am not an expert on either of those. But either way, there's another side to the balance sheet, and at the end of the day, for these technologies, we need it all. To get to this 1.5, it's not like we only need LNG or we only need renewables. Phase out coal is a big one. We're going to need all this stuff. And that's what both the IPCC and the IEA are saying, and they're showing these transitions. How do we increase one and decrease another? And then on the other side of the coin, the sinks, increasing our sinks in the world, particularly the IPCC report talked about this, but so did the IEA. We need all of this too. So it's not a and or, it's like an and. And I think that's where I end up. And it's interesting that it's actually the US in the Larson cartoon here, because of course they pulled out of the Paris Accord. And I'm not saying this is our guys in Victoria talking. I have to give them more credit, but it just says, gentlemen, it's time we gave some serious thought to the effects of global warming. This is a 1985 cartoon, so just for information. Okay, that's the end of my morning thing. Thanks for staying with me, everybody. That was a lot of information. But the idea is it's meant to set up for these discussions on the pathways the energy pathways, whether it's IPCC or IEA, and what they're saying, where do we need to go in this transition, in this journey. But yeah, that's the fundamental science of it. The climate is always changing. We don't like where we are right now. We need to be part of the solution. I think Canada has a lot to contribute there. That's another piece we'll have in the next part of the conversation.
So any questions or comments from the folks on the phone?
One data point for you, I was just looking while you were asking the question, because one of the things when you talk about renewables being cheaper than fossil fuels, it's a bit of a false statement sometimes. On a pure capacity basis, it's actually true now. The problem is you're comparing intermittent energy with firm energy, and that's why that coal plant picture I showed you is such a compelling picture, because the point that was just made about, we all want more wind and more solar. Like, I can't find any, other than crazy people, like everybody thinks that's a good idea. The problem is what was just stated, and to drive the point home, Alberta is very, very proud, and we've been hearing a lot in the news about the Alberta wind auction. Alberta has actually done some amazing things to bring wind into their grid, and have shown that they're actually buying wind at $30 or less a megawatt hour, which is pretty darn cheap and cheaper than a lot of other fossil fuel choices. But the problem is that the wind doesn't always blow, and I looked it up just while you were asking the question. So literally 2 minutes ago, 94.37% of Alberta's electricity is being produced by fossil fuels. Wind is at 11.79% of capacity. So this is what my point about installed capacity for wind is huge. But right now in Alberta, it's running at 12% of its capacity, producing only 1.97% of total generation in Alberta. So all of the wind in Alberta right now that's installed is generating less than 2% of the total generation in Alberta while we're sitting here talking. And solar is, all of its installed capacity is running at 0%, like they're generating zero. So this is the dilemma that coal is and that LNG provides, which is you need that base load generation, because the good people of Alberta still need the lights on today, which is why 95% of their energy right now as we speak is still coming from some form of fossil fuel, either coal or gas. And this is BC's ace in the hole. Right now as we sit here in BC, 99+% of our energy in BC is being generated by 100% clean renewables. And that's our ace in the hole. And we talk about generating